This is an now this is an example of ill-posed problem, just to have an idea. So this is the Laplace equation with two initial conditions. F is 0 and G, it is 1 over n sine nx. So using separation of variables, this problem has a unique solution, and this is the solution: 1 over n squared sine nx sine hyperbolic ny. Now, if we look to F and G as two inputs, and sometimes we don't have these inputs exactly, and we need to measure these inputs using some instruments. So here F is 0, and this is 1 over n sine nx, which is less than 1 over n. So the maximum error in F plus G, it is 1 over n, which goes to 0 as n goes to infinity. But if you look to the solution is, this is the solution here. The solution here, it is 1 over n squared sine hyperbolic ny. The solution here. This is the maximum solution because the sign is less than 1. So this is the maximum or the upper bound of the solution. It's clear that as n goes to infinity, the error goes to 0, while the solution goes to infinity, which means that small change in the input data on the function g, a small change, for example, 1 over 100 or 1 over 1000, which is small error in the measurements, will lead to a very huge error in the answer or in the solution. So this is ill-posed problem because small change in the inputs will lead to a huge change in the output answer. Another well-known example, it is a numerical differentiation. We know from numerical that numerical differentiation is ill-posed problem. This is an example to show this. If we have the function 1 over 1 plus t squared, this is the function here. And suppose that when we measure this function using an experiment or using experimental measurements, we have a small error or small perturbation where delta is sufficiently small. For example, we will take here delta 10 to the power minus 10. So look to the error here. It is less than delta, which is less than 10 to the power minus 10, which is very, very, very small change. So which means that y delta and yt, they differ slightly, and y delta differs slightly from y, small perturbation here. Now, if we apply this, the forward formula for approximating the derivative yt plus h minus yt over h, now if we apply it on y of t, we will get, this is the derivative. This is the derivative. But when we differentiate this function with the perturbation or small perturbation, we have this function, which is in blue, which means that small change in the measurements or the input data leads to a huge or catastrophic variation of the solution. So here, the confusion or this confusing case occurs when the function y is the result of experimental measurements. So we don't have y, we need to measure y, and because of the errors of measurements, we have small perturbation or small error less than 10 to the power minus 10. Now here we find that a small change in y leads to a huge or a big change in the output. So numerical differentiation is an ill-posed problem. Now, mathematically, we can organize this as follows using operation or operator theory. So what we have here, the problem is we have fx equals y, f is an operator, and let me say now that the f is a linear operator, and we can modify or generalize all the talk about nonlinear models. So if we have fx equals y, and this is, suppose that now we have y and we want to find x. So we have y and we want to find x. So existence means that for every y, there is at least x such that f of x equals y. Mathematically, existence means that the existence of a solution of the inverse problem requires that the function f is onto. Now, what about uniqueness? Uniqueness means that for every y, there is at most x with f of x equals y. This is the definition of one-to-one. And stability, for example, stability means that small change in the in the values of y will lead to small change of the answers of x. So if you look to this, this corresponds to that f inverse exists and continuous. So mathematically, onto means that existence, injective or one-to-one means that uniqueness, and f inverse exists and continuous means that stability. So when we study the problem, this inverse problem, given y we want to recover x, mathematically, the problem is well posed f, the function or the operator f is one-to-one onto, and the inverse of this function is continuous. So in this case, we have an ill-posed problem, oh, sorry, well-posed problem. Now, when we talk about these three properties, one-to-one, onto, and f inverse is continuous, we know that this depends on x and y and the operator f, especially because we are dealing with the spaces x and y. Maybe they are norm spaces, maybe they are Banach spaces, maybe they are Hilbert spaces. So the injective or the nature of the spaces and the operator will play a major role on determining whether their function is one-to-one or onto. But so properties of the spaces and the operator decide whether this problem has a solution or a unique solution. But if inverse is continuous here, this requirement is related to the topologies, not only about the operators, because we will talk about continuity. So we have to talk about the topologies of these spaces. And for example, this depends on the spaces and the topologies of the spaces. For example, if inverse is automatically continuous, if f is linear and continuous, and x and y are Banach spaces. This is a direct application of the open mapping theorem, for example. But this is not always true, but only if x and y are Banach spaces. So the nature of the spaces and the topologies will play a major role of determining mathematically if the problem is well posed or ill posed. So this is mathematically. So usually, if we have the problem given y and we want to recover x, so the problem solving ill-posed problems is more difficult to solve than the direct problems or than the well-posed problems. The problem here is that we need to estimate variables from indirect noisy measurements. And sometimes we have to recover a large number of parameters. And there is no way to overcome the difficulty of the stability, because usually in ill-posed problems, we have sensitive errors where small change in the experimental data or the outputs will lead to a large change in the solution. So usually all or the majority of inverse problems are ill-posed in the sense that they are not stable. They are not stable. So what we will study or focus here is we will study this problem. So we have if x equals y, y is given and we want to recover x. Now, y is given, but sometimes we don't have the exact values of x, and we will measure the values of y using instruments, and so we have some errors. So we will say that the error in the measurements is less than some delta. So delta is called the noise level. So this is the problem here. So in almost all the problems, we will get y from measurements, so we don't have the exact values of y. So we expect to have small errors in measuring the values of y. So we would say that we don't have y, but we have y delta. So let's say that the problem here is, in ill-posed problem, is that we don't have stability, which means that if exists, there's no guarantee that it's continuous. So f inverse of y delta may be converged, but will not converge to the exact values. So this is the problem here in inverse problem. So this is the problem here. So in ill-posed problems, if f inverse exists, there is no guarantee that it is continuous, which is the case in almost all the problems. So there is no guarantee that f inverse of y delta will converge to the exact solution. So this is the problem. So how to overcome this? Small change in the measurement data will lead to a huge change of the solution. So we cannot use the well-known techniques. We cannot use the well-known techniques, because when using the well-known techniques, we have to deal with y delta, and this is not y, so a small change in y will lead to a huge change in the solution. So this is the problem here. The idea is using regularization. Let me just give the idea of regularization in inverse problems. Let me go back to the same problem, which is a numerical differentiation. This is the same problem we talked about a couple of minutes before. So we used here to differentiate the function the forward difference formula, this formula, and this formula gets more accurate as h goes to 0. Okay, and the definition of the derivative motivates this formula. And from numerical analysis and using Lagrange interpolation, we know that the maximum error in using this formula to approximate y prime at t naught, it is this term, mh over 2, where m is the absolute maximum of the, absolute maximum of the second derivative of the function. Now, if we look to the y prime at t naught and minus, this is the exact value, and this is the numerical value, or the value obtained by the formula, but we don't have y, we're using y delta. So this is less than or equal, we add and subtract this term. Using the triangle inequality, we will get this term. The first one, which is the error of the formula, and the second one, it's easy to get it. It is 2 delta over h. It is 2, because we know that y minus y delta is less than delta. So this is the idea. What's the problem here? So there are two terms that control the error. The first term, which is the approximation error. The approximation error. As h goes to 0, this will go to 0 and the approximation gets better. But what's the problem? Here, it is the measurement error or the data error. As h goes to 0, this will go to infinity. So this is the problem. This is the problem. So if we choose a small h, we will get more accurate solution. But there is no guarantee that this accurate solution will go to the exact solution. And if we have a very small h, we will have a damping here. We will have this damping here. So what we're gonna do? We have to choose h in a smart way to balance the two terms, to balance the two terms. So we need to balance the approximation error and the data error. For example, look at this. We can choose h, for example, square root of delta. For example, delta here is 10 to the power minus 10, so we can choose h 10 to the power minus 5. So in this case, this is small because h is 10 to the power minus 5, and this is 10 to the power minus 10 to over 10 to the power minus 5. This is 10 to the power minus 5, which is a small quantity. So we have two small quantities, and this is the idea here. With choosing delta 10 to the power minus 10 and h 10 to the power minus 10, we have the problem. But when using h square root of delta 10 to the power minus 5, look to the exact and the dotted solution. It is what? Y delta, the derivative of y delta. So here we solve the problem. So the problem here, we have a parameter h, and this is, it plays the role of a control parameter. We need to balance what? The approximation error and the damping error or the data error. So if we choose h in a smart way, we can balance this and we can get a good solution, and we can get rid of the noise amplification. So this is the idea of regularization. Regularization, you have to impose a parameter, and then you have to choose this parameter in a smart way to balance the approximation and the approximation error and the data error. So this is the case always when we are dealing with ill-posted problems in math. So keep this in mind. So mathematically, if there is in the literature, the mathematicians, they developed a solid theory about regularization, and we have now books talking about theory of regularization. There are a lot of theorems, a lot of references and books that are talking about regularization or theorems to how to ensure that this regularization can be is working, or you can always choose such control parameter in a good way. Just I will give you a short account, because here you have to go to the full theory, and we don't have enough time for this. The idea is very simple here. This is the operator f from x to y, and x and y, say, for example, Hilbert spaces. So f inverse is not continuous, which means that there is a problem in stability. We don't have the third condition of Hadamard. Small change in the data will cause a small change in the inputs or the solution. So the problem here, if inverse y delta, there is no guarantee if you use the inversion of the operator f. For example, if you are talking here about matrices, maybe you can use the inverse of the matrix, but the inverse of the data, or the data with errors, there is no guarantee that this will converge to the exact solution. This is the problem here. So what are we gonna do? Regularization in mathematics means that you have to bring a continuous approximation of f inverse such that this continuous approximation converges to f inverse, which is an approximation of f inverse, but it is a continuous approximation. And then this approximation depends on a parameter, say it alpha. Then after that, you have to choose alpha in such a way that R alpha of y delta, this is the continuous approximation, converges to the exact solution. So you need continuous approximation of inverse and good choice of the parameter. This is regularization. This is regularization. And when you choose the control parameter here, it's very important to mention that it should depend on delta, on the noise level. It should depend on if it is constant, so this is not regularization. And we will talk about this later. So let me give you here an example. So this is AX equals Y. A, it is this matrix, and Y, it is this vector. So if X is given, and we want to find Y, this is the direct problem. So we have to multiply A times X. This is the answer. So this is one. Now, what about given Y, you want to find X. This is the inverse problem. So the answer is 1, 1. So we are fine. Now look at this. Suppose that we have a noise error with less than 100%, which means that we don't have the exact value of Y, but we have a measured value of Y. Instead of 3.98, we measured it as 4, and instead of 2.1, we measured it as 2 because of the errors by the measurements or the instruments, for example, which is small error less than 100%. Now, if you solve now the problem, X equals A inverse Y delta, this is, you will get surprised that the answer minus 200, 200. And the exact solution is 1, 1. Look at this. Small change less than 100% leads to a catastrophic answer, which is an answer away from the exact solution 1, 1. So this is ill-posed inverse problem. So in mathematics, we know that using matrix inversion is not a good idea to solve a system because that this inversion affects by the small changes in the data. So what's the idea? Tikhonov in 1963, he gave the solution of this problem. He said that go and take this A transpose A plus HR identity inverse A transpose Y delta. By what? By minimizing this problem. He minimized what? Two terms. What's that? The residual, which is the error, and this means that we are choosing the smallest norm of the solution, or X, the solution with the smallest norm. This means in mathematics, we are looking for the smoothest solution. So we are looking for minimize this problem, and we are looking for the smoothest solution. By solving this, minimizing the problem, he finds the normal equation. This is the normal equation. Then there is a parameter here in the normal equation, which is H. And here, if we change H, we can find some values, small values of H are bad choices because this is the error. For example, if we choose H1.175, we will get a good answer. 0.2, we have a good answer. 0.6, still we have a good answer. And large values of H, we will get bad answers. So the idea here is, if we analyze the error, we have the error here is two terms. Data error, approximation error. If H is small, the approximation error gets small, but the data error will be huge. And if we have a large value of H, we will get small data error, but the solution will be away from the exact solution. So in this problem, so we have good choices of H and we have bad choices of H, and we need a criteria to choose a good H. For example, here, if we choose H.2, so we will get a good answer because the error will be 0.007, for example. So this is another example of, here we imposed again a parameter H. This H will control the problem, but just we need criteria how to choose this H. So let me just go quickly to the idea of regularization. In regularization, instead of minimizing the residual, we found that minimizing the residual causes many problems, and this is a high oscillation in the solution of this problem. And we don't have a unique solution for this problem. So in mathematics, we don't like to minimize the norm discrepancy or this term. And instead of that, the idea of Tikhonov is to minimize the residual, plus we are looking for the smoothest solution. In this case, if we minimize this instead of this, the benefit is here. The first condition is we are looking to small residual, which is the first one, this one. Here we have infinitely many solutions. But if you are looking for the smoothest solution, which is with the smallest norm, so this problem now has a unique solution. So mathematically, instead of minimizing this problem, we minimize this problem. So we minimize the error, taking into account we are looking for the smoothest possible solution. So this is the idea of regularization. Now we have here a parameter lambda. Lambda is called a regularization parameter, and lambda will play the role of controlling the balance, the approximation error or the data error. So here we have some issues why we don't prefer to minimize the residual, because we have many problems we talked about, and instead of that, we talk about minimizing the residual plus and looking for the smoothest solution. Here we have a mathematical definition of regularization. Regularization means that you are approximating the inverse of the operator f by a continuous approximation, and you have to make sure that if you choose data close to the original data and you have an error with noise error delta, then you have to make sure that the inverse of y delta will converges to the exact solution of the problem. But here you have to choose delta, the control or regularization parameter in a smart way, so you can control or balance this. So when you choose the parameter choices, so we have, we need to talk, there is a theory about this, and maybe later I will talk about some of the methods used to choose the parameter or the regularization parameter. But keep in mind that always this parameter should depend on the noise level. Should depend on the noise level. And in some experiments, they choose lambda such that it depends on the noise level and even on the measurement data. And there is something here that so about regularization, there are a lot of types of regularization. The most used or well-known regularization methods are the Tikhonov type regularization, and we have the iterative regularization methods in Banach spaces. So Tikhonov type regularization are the most used methods, and the theory of these methods have been developed, and there is substantial progress in the theory of these methods in the last decades. So this is the first problem by Tikhonov. Tikhonov is a Russian mathematician. He's really great mathematician, and still till now we are using the same idea of regularization for solving all ill-posed problems or ill-posed inverse problems. Tikhonov mentioned the theorem in 1943. The theorem is, if we have a linear operator a from x to y, and here a, the domain of a is a compact set M, and and N is the range of Mx, which is N, which is a subspace. So and then the inverse mapping, A inverse, is continuous on the set N. So here, the problem here, all what we need here is that we need to know that all the solution should belong to a compact set, and the output should belong to AM, which is a subset of Y. So when we take measurement, in this case, A inverse is continuous. So according to this theorem, to ensure that your problem is well posed, you have two requirements. The first, the solution should belong to a compact subset M of X. Second, the second condition is that all the values of Y delta, or the measurement, should belong to N. If we have measurements outside this interval, there is no guarantee that this is a well-posed problem. So here it's like knowing that the solution belongs to a compact set. It's like a prior information about the solution. If you know that, you can solve the problem. So this is the idea of, in order to solve an inverse problem, keep this in your mind. You cannot solve an inverse problem without more information about the solution or about the input data. You need more information, extra information, or priori information about the solution. Keep this in your mind. You cannot solve an inverse problem without additional information or additional measurements about the solution. For example, in the heat identification problem, they are using a sensor to measure something about the heat on some finite domain. So the idea again is, now what we are looking for, we have measurements of Y, and the noise error is delta. So if we define this set, it is all the solutions X or values of X such that AX minus Y delta less than or equal to delta. So for sure, this set contains the exact solution and contains the approximate solution. But this is a very huge set, and this set contains bad and good approximations. So what's the idea here? Tikhonov started by to minimize the residual, or to minimize this problem. Then after some condition, he proved that the solution is on the boundary of the set S. Under some conditions, the solution is on the boundary of the set S. So he replaced less than or equal by equals to, because under some conditions, the solution is guaranteed to be on the boundary of this set S. Then after that, he started to minimize this problem, and he used Lagrange multipliers. And using Lagrange multipliers will cause will bring the Lagrange multiplier, which is here 1 over lambda, which is 1 over lambda Lagrange multiplier. Then after that, he started to choose lambda such that lambda satisfies this condition. This is called the discrepancy principle. So the discrepancy principle, we choose the lambda such that lambda satisfies this condition, usually. So here, then we started with this problem, and then we have to choose lambda satisfies this condition. So the idea is, Tikhonov regularization is, we need to minimize this problem, and then we have to choose such delta that satisfies this condition. This is the original Tikhonov regularization problem. Here, let me give you just a small example here. This is a discretization of linear integral equation. This is a linear equation, and X is the unknown here, and we want to recover X. In many experiments, we don't have Y, but we have measurements of Y. And if we now discretize this using collocation at ti, for example, so we have here k ti and y at ti, this integral, then replace the integral by a quadrature method, then you will transform this problem into a linear system. We have two problems here. The first problem, sometimes we don't have the exact value of y, but we have y delta measurements. And using the inverse is not a good idea because inverse is ill-conditioned, as we stated, because if we are using a large number of nodes, we will get A will be ill-conditioned or almost singular. We know we have this idea in numerical analysis. And what about if the points we are using for the quadrature, the number of these points does not equal the number of the collocation points? In this case, the matrix is not square matrix. So we cannot use the inversion. So the idea here, while solving this problem, A is not necessarily square matrix. Even if A is a square matrix, if you are using or if the discretization is fine enough, the matrix A is ill-conditioned. So we have two problems here. So if we use the idea of Tekhnov, so we have to minimize this problem. If we minimize this problem, we will, using the least squares, for example, technique, we will get this normal equation. The normal equations will be A transpose AX equals A transpose Y. And because A is ill-conditioned, so it's not easy to find the solution of X by using the inversion. So if we use Tekhnov regularization, for example, this is the Tekhnov regularization, and we start the regularization, we will get this answer. So just we transform the problem into this problem where C and H are like this. So then we have this problem. And we know from a numerical analysis that the minimum or the solution of this minimization problem is this solution. Now, if we go back and use the values of C and H, so we will get this algebraic system, this linear algebraic system. So now, if we choose L, the operator L here in the Tekhnov regularization, either identity, which is one of the choices, and you can choose L in a different way, but to have the zeroth order approximation of Tekhnov, we choose L to be the identity. So if we choose L as the identity, so we have, this is the system we need to solve to find X or to recover X. Now, if we use the singular value decomposition, which is well known in a numerical analysis, we can take the matrix A and write it as VDW transpose, where V and W are orthogonal in this sense. And D is a diagonal matrix which contains on the diagonal the eigenvalues of A transpose A. This is a well-known technique, singular technique. Now, this is the matrix D, and then we can write X in this way now. So this is a very simple way to write because we have all these requirements. Now we can use this to find the solution X. So this is a simple example how to use regularization because linearizing this problem, which is solving linear integral equation, we need to using collocation and then approximating the integral by quadrature technique. We have a linear system. The linear system here, there's maybe A is not a square matrix. So here we can use, by using Tekhnov regularization, we can overcome or we can solve this problem, even if we don't have a square matrix, for example. So we have iterative regularization techniques, which is we can talk about, but maybe I will skip this because we don't have enough time for this. But let me finish by giving this example, which is the last example. Maybe it is of interest. So this is the heat equation. And here, the source term depends only on x, and we don't have this source term. So the problem here, we need to recover this source term. And to recover the source term, we need additional information. The additional information here is by observation at a final moment t equals 1, which is ux1 equals g of x. So we have this. So we have this information, which is the final overdetermination. They call it any numerical analysis. So to recover the function f, we need more information about the measurements or the observation. And here we would use this information. Now, using separation of variables to solve this problem, suppose that we know f. So now we can apply separation of variables to solve this problem, and you will get this solution. This is the solution. And it's very simple, just separation of variables, you will get u of x of t. Now, what about, we can define the operator k, kf equals g of x, and kf equals this one. So we get this condition from here, from this one. Should just go and replace t by 1 here, replace t by 1. So here we will get k f of x, it is this operator, depends on f. So this must equal g of x. So here we have many references, and we can show that here k, this operator, linear, compact, and self-adjoint. So we can find the inverse of this operator, and the inverse of this operator is given in this way. This is from the Fourier decomposition theory. We can obtain that k inverse is this function or this operator. So f equals this quantity. Now, suppose now we don't have the exact value of such g because it comes from observations and measurements. So we have errors in g with noise error, with noise level delta. And we know a priori bound on the heat source. We know that the heat, it is bounded by some number e. I'm talking about this function f, the unknown function. So we have a priori information that this function is bounded by e, for example. And we can measure this by some measurements or sensors, for example. Now we have to solve kf equals g. This is the operator equation. And we can use technique of regularization to solve this problem by minimizing this problem. If we minimize this problem, this is the normal equations. This is the normal equations using the least square technique. Using the least square technique to minimize this problem. So this is the solution. Because k adjoint is k, because k is self-adjoint. So we can write f delta in this way. Just substitution, small substitution. Now look, the f delta depends on lambda. So I will call it f lambda delta of x. We will call it here. So look at this function. This function, if we choose lambda using the discrepancy principle or in a good way, we need some analysis here. If you choose, for example, lambda in this way, you will get that the exact values of f which we want to recover, and these values or this approximation solution, which all the requirements here are given, here we will get the error is delta to the power p over p plus 2. And here, so now if you look again to the problem, Kf equals G, this is Kf. And if we now use the composite trapezoidal rule to replace the integral here, you will get this collocation equation, which is very simple. We collocate at xj, and then we just replace the integral by the composite trapezoidal rule. So here, this is the formula we're going to use. And now we can transform this formula into a linear system. This is the linear system, which is very simple. And again, the values of V, which the V contains the values of F, we are looking for. This is now the formula for in matrix notation. And we assume that the measurements here, the values of G, are subject to some errors, as we mentioned here. So we need some noise, for example, or some perturbation on the values of G. So I used, for example, rand n size, which is like a MATLAB command to bring the random distributed perturbation for the values of G. Finally, we solve this problem. This is the exact U, this is F, and this is G. Suppose that F is unknown, we want to recover F using our idea. So I gave an example, so the exact solution is, we know the exact solution, so we can compare the numerical and exact solutions. You can get, this is for example, the values of F. This is the exact, and this is the numerical, using, for example, with noise level 0.1. And this is with the noise level 0.05, we increase the noise level. And here, this is the noise level. And you can notice that even with noise level 0.1, so still we have a good approximation or acceptable approximations for the recovery of the function f. So this is the idea of regularization, and the subject needs a lot of lectures to talk about, because the regularization theory, it's a huge theory, and it's like a course, and the selection of the parameters, and sometimes in many applications they don't use, for example, the second term in the techno-regularization as the smoothest norm, but they are using some functional operator. So this is just I gave some just or presented just the idea about the topic. And thank you very much for your attention, and the mic is yours, Labrin.
So thanks, Fadi. Very nice talk and good subject. Now I would like to ask
please.
about creation, maybe advance, please, for participations. Okay. How I will.
Can I answer the question? I have a question.
Yeah, please.
Okay.
Could you recommend some book where this material is?
For sure. So maybe I have a list of books, but maybe I will share it with Labrin, and he will share it with you.
Okay. Thank
but
you.
right now,
so why I not see your presentation? Why? But problem maybe. Shariar, what happens? Maksat.
I have a question.
It's still on the screen. I think there is something with your screen. I can see it now on my screen.
but problem.
There is a question, maybe.
Question.
Yeah, someone has a question.
Yes, I'm ready.
Yeah. But can I ask a question?
Yeah, please.
It might be really silly because I'm not familiar with regularization at all.
There is no silly question in mathematics.
The term, the second term which you add, at some point you said it's a different norm.
Yeah.
The choice of that norm, does it affect something?
Yeah. Because I told you this is.
I mean, in different norms, does it produce different solutions? So then the question of existence arises.
Sometimes here, he's talking about this.
Mm-hmm.
Yeah. Sometimes this norm may be possibly a different norm from this norm. Yeah, it's gonna happen. But in this way, you have to have a vast experience in using, for example, the regularization technique. So we have some professors, they have a very good experience on implementing regularization techniques. When they see the problem, they can suggest, for example, the term here. Maybe in some cases, maybe here I'll show you, they don't use, for example, the norm. They are using a functional, not the norm of X. They are not looking only for the smoothest solution. They are looking for something else. So sometimes from experience, you can, for example, decide the functional here, so can make the computational more easy, and you can get more accurate or more acceptable results. Yes, changing the norm will change the analysis. But the simplest case is to choose the norm of X, and it is the same norm as the norm you are using here. This is the Stokhanov idea, which is the simplest idea. Yes.
Thanks.
Oh.
I have a question.
Yeah, please.
Are there any problems concerning nonlinear parabolic equations?
Here I don't have a problem here, but nowadays I'm working on something like fractional differential equations. I'm looking for recovering the source term in the fractional differential equation, fractional heat equation. And we have nonlinear term. Still, we are working on this because the analysis or the theory of nonlinear inverse problems is not easy at all. And I'm trying right now to recover the term because for me, to prove the existence and uniqueness of inverse problem, I don't use fixed point theory. I use something called semi-group approach or semi-group theory. So semi-group theory, it's easy to study or to put the inverse problem in abstract form. Then you are using or you are talking about operators. So nowadays we solved the problem, or we get some results about existence and uniqueness, but using not the classical theory, but using semi-group theory for linear operators. Yes. And what is very interesting, maybe one day we can talk about this. To prove existence and uniqueness of inverse problems, and I tried this and I published more than 4 or 5 papers about this idea. You can use semi-group theory along with perturbation theory for linear operators. Because sometimes when you add a bounded or a continuous operator to a semi-group generator, the result is still a semi-group generator. So still you have all the properties. So sometimes you have to define in a smart way some terms in the equation so that you have what? Semigroup generator, which is the original differential operator, plus some terms, and these terms are bounded or continuous, because generator plus continuous or generator plus bounded, you still have a generator of a semigroup, and all the ideas of the inverse problem works here. So this is maybe a good idea, but a numerical solution of nonlinear inverse problems is not easy. I'm now still, I prove the existence and uniqueness of the problem. I'm working on the numerical, and still I'm stuck there, really. Maybe I need collaboration with some professors or some professors. They have good idea or solid idea about solving nonlinear inverse problems. Especially this is a fractional inverse problem. This is the problem.
Okay, more question. Advance. No question. Fadi, but
yes.
About you said application of semigroups.
Yes.
1 year before, we have one talk in American Mathematical Institute of Science last year. Section Zahar Nashid, inverse problems. We have some collaboration work. It will be better to see, because we have some good idea.
Yes.
Maybe useful, and this subject very with my interest in future. I will contact with you, Fadi.
Yes,
and
that's good.
But my thanks for you. Not more time. I meet with you here in multiple university. Now, 3 different talks I listen from you, and great success.
It's my pleasure.
Yeah. So very nice to meet you. I hope our continuation in future.
I hope so.
So no question. Thanks for your very nice talk.
Thank you very much.
This is very nice after our conference Antalya to be my participation here. Thanks for all participation also. I hope your support and contacts with us, and we will continuation our seminar talk in future. See you.
Thank you very much.
Thank you.
Thank you.
Thank
And
you.
I hope you sent for Maksat your talk, because we will put it in video, okay?
Yes, for sure.
Арсен, жду. Когда будет, давай, я жду вас.
Спасибо.
Не за что.
Thank you. Very nice talk. Thank you.
Thank you. Thank
Thank
you.
you. Very nice.
You are welcome. Thank you very much. Bye-bye.
Thank you.
Bye-bye.
Thanks.
Oh, bye.
Bye.
Bye-bye. Bye-bye.